It's like 70 pounds. No, it's only 50.
Just from things adding up, or point specific?
No, I want some drink.
Ah, yeah, yeah.
Just right.
Yeah, you could have drink tickets.
No. Probably over 500 cents.
What age is he?
25.
25. He's his own. I hate these people who are really joking. He's younger than me. Josh and stuff.
Yeah, I used to be like that, but then this is not good. In secondary school, I was always younger than everyone I was before I stopped doing it. I just started school when I was 3 years and 11 years. And then I did 4 years. It wasn't a mistake, it was great.
No, 4 years ago, correct.
It was great here doing absolutely nothing.
Yeah, exactly. You barely get through your life, so.
I think as well in England because they do 3 undergrad years.
Yeah.
If I was in England, I would be a year.
Some of them are so young, I can't get over it. Like.
He's back. He's back. He's back. Yes.
Yeah.
I still don't know why he was in Costa Rica.
It's definitely
Smoking? No. I mean, there's already one physicist in jail in Argentina for smoking cocaine. Yeah, he was going to. He's an American called Paul Frampton, and he was going to meet a woman he'd met on the internet. And she claimed to be a supermodel, but then he turned up in Argentina and he met one of her relatives. He said, "Oh, we just need you to fly to a different city. Can you bring this briefcase?" Okay.
Oh man.
So he's still writing papers, and he's like in the prison for the hospitality.
So
He says it's great, he's lots of time for research.
I guess that's true.
It's operations.
His PhD students have to follow him. So there might have been a woman which was in collusion with a bunch of drug smugglers who seem to have gotten off scot-free from this.
I guess it's one way to get people to read your papers. Like.
He's crazy. He's one of these guys who has decided that he solved everything.
Who is this?
A guy called Paul Frampton.
The name rings a bell.
Yeah, well, there's a musician called Peter Frampton.
Yeah,
but that's
that's
not
what
him.
I'm thinking.
I mean, there were news articles about him back when he was arrested for drug smuggling. So. I hope this isn't all being recorded. It might be like.
Yeah, what you said about the drug smuggling may be true, but his papers are true.
Yeah, that's the thing. Well, you have to be diplomatic about that. But he's unlikely to be offering postdocs in his Argentina. I don't think I'm too worried about it. Okay, it's just gone 2, so let's start the first session of the Theoretical Physics Part 3 seminars. So our first speaker today is Carlos, who's going to talk about fiber bundles and gate theories.
So, good afternoon, everyone. As you can see, I'm going to talk about gauge theories, and in particular, I would like to introduce a mathematical structure that underlies gauge theories. And because we all know something about gauge theories, at least in the QFT and symmetry lecture courses, we've seen several applications and several examples of gauge theories. So, I just wanted to present the mathematics that makes everything sort of coherent and beautiful, in my opinion. So let me outline this work. Let me outline what the plan for today is. Sorry. Okay, it's working. So, what I want to do today is first present Maxwell theory as a very simple example of the gauge theory, and then introduce a fiber bundle geometry, which is, so I will give some basic definitions that hopefully just with a differential geometry taught in GR should be enough. And then I will introduce what a connection and a principal bundle is, which is the basic object that gauge theories deal with. And finally we'll find gauge theory in the most general setting. And in the end we will formulate EM, Young-Mills and gravity as a gauge theory. And some final thoughts. Okay. So this is electromagnetism, we all know from, probably high school physics. And so let me just rephrase it in a more compact way by using the language of differentiable forms on Minkowski space. So we encoded magnetic and electric fields and the currents and the potentials in nice differentiable forms, totally antisymmetric covariant tensors. And also we introduced exterior differential and exterior co-differential that are just first order differential operators that has this nice property of nilpotence. And we write all the Maxwell equations in this very compact and nice way. So let us focus on the field equations that don't involve matter. As I wanted to say that I will not focus on the interaction between fields and matter in this talk, because it's a rather lengthy discussion, and I will come to something in the end. So let us focus on this equation. And of course, if we choose a potential and define the field, electromagnetic field in this way, the equation is identically satisfied because of the nilpotence of the exterior differential. And so, if we pick two different potentials, initially we might think that the two electromagnetic fields will be different, and indeed they are different in general, but if they're related with this specific equation, so with an arbitrary function here, this is a zero form of a function of no space-time, then we see that the electromagnetic potentials are the same. So they represent, and indeed electromagnetic potentials, the electromagnetic fields are the same. So they represent the physics, they represent the electric and magnetic fields, and so the dynamics of the particles are moving in space-time. And so it's indeed an ambiguity or symmetry of our theory that this choice of potential is not unique. So let me move into the geometry, and I will spend probably 20 minutes just talking about geometry, hopefully to let you know the basic ideas, or at least show you that the basic ideas in principal bundle geometry are actually quite intuitive, and they're easy to understand just with usual differential geometry that you need for GR, for example. So the main object of gauge theory is a fiber bundle. So what is a fiber bundle? A fiber bundle is nothing but, a fiber bundle is a sort of generalization of a Cartesian product of sets or of manifolds. So in the way that you define a manifold as a generalization of an affine space, and you make it, you only constrain it locally, you look like an affine space. A fiber bundle is very much like that. It's a is a manifold, it's got a special property that locally it looks like a direct product of two underlying manifolds. So we'll use a black box for this, and so we need, there are quite a few ingredients to define, properly a fiber bundle. So let's go systematically. So we need, first of all, I will use this three-dimensional, two-dimensional, one-dimensional kind of picture because it's nice because I can draw it. So let us consider a three-dimensional manifold, which is indeed an arbitrarily dimensional manifold, but for example, we'll look at a three-dimensional manifold. Call it P. This is a total space. This is just a differentiable manifold. Then let us consider another manifold, M. It will be the basis space. It's another manifold. Then let us consider another manifold, which is the typical fiber. This is fiber. And these are, in principle, arbitrary differentiable manifolds, but they're not arbitrary when we consider the definition of the fiber bundle, because there should exist a map, a projection from B to N that is surjective, and such that if we take an arbitrary point of N, lowercase n, then the inverse image of N, which by regularity this submanifold of B should be diffeomorphic to F, right? And so this is called the fiber over M on B, and this might look something like this. All the points are projected onto the same point on M. So this is the basic idea of a fiber bundle, right? But since, obviously, a set of this kind, this is a fiber bundle, but this is a trivial fiber bundle because the projection is just canonical. It's just the trivial one. You just take that part. So, in order to make this general and make it interesting, we need to introduce a bit more machinery, and this is the structure group in the first place. So the structure group is a Lie group, so again another manifold, G, that has an action is effective on F. So that given 2 points of F, we can relate them with an element of the group by means of the action G on F. And then finally, what realizes the fiber bundle as this notion of being a generalization of a Cartesian product is that locally it looks like a Cartesian product, and this is done by means of a trivialization. Trivialization is essentially, you can imagine it as the atlas version of a fiber bundle. So it's a set of maps from open sets of the fiber bundle into the direct product of the projections of those sets and the typical fiber. So it is indeed the version in the analogy is the atlas for our fiber bundle. So I will go into the details of the trivializations, which are a bit technical, but the key point about trivialization is that when we have two overlapping trivializations, in the intersection we can translate common points and fibers with the group, any element of the group. So this is the basic idea of a fiber bundle. So in particular, we were interested in principal bundles, and this is just the restriction of a general fiber bundle. So it's a specific case of a fiber bundle. So if you get a notion of what a fiber bundle is, you certainly have a notion or intuition for what a principal bundle is. And this just puts the structure group in a much more prominent place. So you just give the group much more importance. And then, indeed, what you define is a group G, well, what you consider as a group G that has an effective action on B, an action on B, such that every single orbit is diffeomorphic to the group itself. So we consider, and then you only actually require that, and then everything comes naturally. So all the orbits are all the fibers are generated by acting the whole group. So the orbits of the group are actually the fibers, and then the projection is the canonical map from this total space to the quotient space with the equivalent relation being belonging to some of the orbits. So all the firebundle structure races there naturally. If we consider an action of a Lie group on VSP with a specialty that every orbit is diffeomorphic to the group itself, and indeed the typical fiber of a principal bundle is the group itself. So yes, fibers are orbiters. Now let me give you a very intuitive and probably very silly example of what a fiber bundle looks like, but let me consider that trivial spaghetti fiber bundle, right? I mean, this is precisely what, when I first think of fiber bundles, I picture something like this. I have a bunch, and that's my total space, and then the total space is made up of, fibers. And this is rather, this is, you can imagine these are lines, and you're just arranged in such a way that you clearly see that there's this underlying structure. But what happens when you cook it, and you cook it properly, so you burn it or you stir it or something, then you get something like this, a non-trivial spaghetti bundle. And this is a sort of generalization that we want to address by defining fiber bundles. Why just don't stick to this sort of sets? Well, because we want to do some interesting things like that. Or, if you're a physicist or mathematician, something interesting like this, like a tangent bundle of a sphere. So the tangent bundle, this is a pictorial representation of a tangent bundle of a sphere. And you can see the tangent bundle of a sphere, probably you met that in differential geometry or GR, is just the joint union of all the tangent spaces of the sphere. So effectively, the union of all possible tangent vectors of the sphere. So if you picture a sphere there, that surface, you get at every single point, all the possible arrows emanating from that point are indeed the tangent space at that point. So you could imagine, a sector of this tangent bundle as being lines in this way, and every element of the total space would be an arrow, so a tangent vector. So, for example, the structure group of this fiber bundle is naturally GL2, because it's all the possible transformations of vectors, and you can see very graphically the action of that group here, which means, okay, if I have that vector, which is to be there, and then I have this other vector, which will be there, it's just a rotation from one to the other, so it's just moving along this line. It's just some pictures for you to get the intuition, basic intuition of fiber bundles. Now, let's talk about connections and principal bundles. So, the very first idea is that when we have a principal bundle that is generated with an action of a Lie group, verticality is already encoded in the model. So, the group in this pictorial case, so I will actually show this picture. So this picture, you can see that in the same analogy. We have a structure group that should be the real line, so just the additive real numbers, and then R2 or something like R2 and then R3. So indeed, the Lie group acts on every point and then generates fiber, and so the tangent to that fiber, in this case just this line, is defined by the it's defined already in the setting of the fiber bundle. So the notion of verticality is already introduced, but so horizontality is not inherent to the fiber bundle. So you need to make a choice. You need to say, okay, I need some complementary subspace at every single point, such that I recover the notion of horizontal, in the sense that it is complementary to the vertical one, which is already here. And this is precisely what a connection is. A connection is just a smooth assignment of horizontal spaces. So, why we use a connection form? Well, let me briefly, this could get really technical, I don't really have the time, but I just want to emphasize that understanding why we use Lie algebra valued one form to encode horizontality is reasonable, and it's actually intuitive. Well, if you picture the vertical subspaces at every single point, that is effectively the Lie algebra of the group. Why is this? Well, remember that the group itself, the fiber itself is the group. So the tangent space of the fiber is the tangent space of the group. But moreover, the group has an action on itself, and at every single point you have the whole set of possible actions of the group. And so you have the identity in particular, and so you have all the possible actions from the identity, and that is locally, and so when you compute that or you define the tangent space, that's the Lie algebra. So the vertical the vertical subspaces at every point of the bundle are diffeomorphic to the Lie algebra of the group, and can be canonically identified with the Lie algebra of the group. Now, what this forms as, well, once we have some horizontal space assigned to that point, what we do is, okay, if it's actually a horizontal space in the sense that it's complementary to the vertical, then there should be a unique decomposition, a vertical component and a horizontal component. So that connection, so that is a map that at every point gives you the vertical component, but not as an element of a tangent space of the phi bundle, but as an element of the Lie algebra. As we saw, these are isomorphic, so it's reasonable. So that's why a connection is a Lie algebra valued one form. But it's actually, in the setting of the geometry of the bundle, it's actually just a projection on the vertical subspace. So it's kind of measuring the horizontality of a vector. If it gives 0, it's horizontal, for us to speak. Then, since it's a one form, we can define, well, we have all the exterior algebra for forms on our principal bundle, but we want to define a differential or a derivative that in some sense recovers the horizontality that we already introduced. So if we define a map, H, that takes the horizontal part of a vector, so effectively, projecting and then subtracting, or an easy way of, just taking the decomposition, the horizontal decomposition, then the covariant derivative is just defined like this. So this is the exterior differential on the phi bundle, goes with H, and H acts on every argument. So, this is shorthand for something like, if you have a form acting on some vectors, then this is the exterior derivative of the form, and the vectors acting with the horizontal projection. Okay, just don't want to comment any more details about this, but you see there's a nice geometric formulation, and it's actually quite straightforward, and there are very technical points, but it's variable, and it's quite beautiful in my opinion. And then define naturally, the first one form you can think of is the very one form that you consider in the first place, and define the curvature as the covariant derivative of omega. So, what are the essential ingredients for gauge theory? Let's go back to physics and our main interest. So, we are to build a principal bundle and give a connection on that principal bundle. That's the essential procedure of our gauge theory. So, what will be the base manifold? Of course, space-time. That's where we always want to end up. We want to recover some results in space-time, so that's our base manifold, where everything will get projected and eventually we'll recover any observations that we have. Then the structure group will be the gauge group, so the symmetries and redundancies of our system. So in the case of electromagnetism, it was this choice of gauge, which was a bit unclear, at least to me. It seems just a function. What is this exactly? We'll see in a minute. And finally, the interaction fields of your theory will be encoded in this omega and uppercase omega. So essentially just omega, because remember that we define this horizontal projection by means of omega, and then these are already in the geometry. So essentially all the interaction is encoded in just one object, which is a Lie algebra valued one form. So from that perspective, it looks very simple. It's just one object. You've got all the information encoded there. So let us, and then we have this relation that will be useful for showing some results later. That since this is a special case of a one form for a covariant derivative, you have this nice structure. So the usual exterior differential and some terms that you might say, well, that's obviously zero because it's a wedge product of two forms in the same form. But these are Lie algebra valued forms, and these are vector valued forms. It's not exactly the same, and the wedge is not identically vanishing when the arguments are the same. So, let's recover electromagnetism. Electromagnetism for space-time, that will be always the case. And we have the structure group. So we all know from QFT or previous lecture courses or wherever that the gauge group is U1, so the complex phases. But why is this? I ask myself, why U1? I mean, obviously, if you're thinking of quantum mechanics, you say, yeah, it's complex numbers, everything's fine. But I like to regard it as SO2 because U1 and SO2 are isomorphic, and I like to think of that because when you find the solutions for Maxwell equations, if you recall, the ones without considering any matter, which is the case here, you find this redundancy or the polarizations of light. So it's not a surprise that we use U1 after all. And so this is the example I came up with to explain why U1, maybe I'm completely wrong, but at least it's diffeomorphic, so it couldn't be very wrong. And yes, so interacting fields will be A and F, as we know from other lectures. And but now recall that this is a one-dimensional line. So the tangent space or the Lie algebra is one-dimensional, and so a one-dimensional vector space is effectively just R. So a Lie algebra valued 1 form in this setting is just a differentiable form. So it's an R valued 1 form, which is just a differentiable form. So this is the usual Wedge product, and so that's 0. And so we recover the equation that we wanted. Just from the, I mean, this was that is the action of this covariant derivative. So this is just purely geometric, and then we recover the equations for electromagnetism. Like that. So I think it's quite nice. Another example is Jack Mills, which is a straightforward generalization of this, is that we use exactly the same base manifold as usual, and then we choose a generalized U1 group, so we consider UN. So but now the connection forms are no longer R values. They are Lie algebra valued. So in case of U2, you have quite big Lie algebra, well, big compared to just R. And so now these terms here, they don't vanish. And you might say, well, that's an inconvenience, but actually that is what allows us to compute interesting dynamics for theories that are not just electromagnetism. So indeed, this is the case for weak interaction and strong interaction. So those are nonlinearities because at the end of the day, you get products of components of A when you work in coordinates, and those are nonlinear differential equations, and then you get some interesting phenomena that you could account for, so, that you couldn't before with just electromagnetism. So let's change into general relativity, which might be a bit surprising at this point. We're considering field theories, classical field theories, but oh well, I should point out that in both Yang-Mills and electromagnetism, except what the base manifold and the structure group is, but not the whole fiber bundle. The fiber bundle is just trivial. The fiber bundle is that times that, simply that. Okay. I mean, in the initial formulation, I will see in the end that there are very nice considerations afterwards. So in general relativity, again, we have the vector space for our space-time, and then the structure group, of course. What's the gauge freedom in special relativity? So it's the principle, the general covariance principle that Einstein imposed in the equations in the first place, 100 years ago. So, and the local version or the pointwise version of that group, which means that you can choose any coordinates you like and you will get the same physical result, is indeed GL4, which is an arbitrary change of basis on your tangent space. So since the fiber bundle structure already encodes the global notion of transformation, which will come in a sec, as a gauge transformation, you only need to care about pointwise symmetry groups. And in this case, a freedom of choice of coordinates is reflected in having a freedom of GL4, so any possible basis on your tangent space. And of course, the connection encoder, so this is just notation at this point. I mean, it's not I mean, it's not a change. I mean, it's quite reasonable why I chose gamma now, because I'm expecting to recover the connection and the Riemann tensor. But at this point, there's just forms on the frame bundle, which is the name for the general bundle of this kind, which is non-trivial in general, not as in the Young-Mills case. And so you see that equation and you say, well, okay, that's just changing the names for the variables, change them for the objects. But if I write that in a local chart, which is actually the case because the trivializations of this bundle are actually an atlas, because this is a frame bundle. It's essentially how it's defined. So if I write that in components, you will see this pattern, complicated pattern. If you remember the GR lectures, that's essentially, well, it's exactly the definition of components of the Riemann tensor in terms of the connection, of the components of the connection. And at this point, I didn't prove it because this is not actually a Riemann tensor or a connection on spacetime, because this is living on the fiber bundle. But this should point towards that this is a, I mean, hopefully you see this is a good setting for general relativity, because we have the kind of objects that we like, right? So this is just an indication. There's no way formal proof that general relativity is defined in this way or recovered in this way, but it's just a strong hint that it's the right way to go, because we have essentially the same objects. So up until now, I was defining objects living on the fiber bundle, so on the whole space, total space, and that's a rather abstract place to be, because we don't measure things outside of space-time. So we have devices to measure stuff on space-time. So we could make sense of fields and scalars being defined on space-time, but not outside of it. So how do we come back to our space-time? So first of all, let's introduce what a Gates transformation is. It's this mathematical language definition, which I don't recommend that you care too much about. It's just the maps that leave the basis point fixed. So it's basically moving from one place to another. Essentially what this does. It's not a surprise that that was called the Gates group. So equivalently, if you take a neighborhood of the basis space, you could regard that as just a g-valued function on that neighborhood. Because remember that the elements of the group act on every fiber, and then if you have a value of the group, so an element of the group assigned smoothly at every point of the space, effectively what you get is something that changed only, in the whole cylinder, in the fiber bundle, that changed points in such a way that they belong to they are projected back to the same point. So but the projected points are remaining changed. Okay, so this is just and this is the usual way that we define Gates transformations. In the physics language, this is a local Gates transformation, which depends on the point of the manifold. And of course, the global is just a particular case of that. So, how do we go back to our base manifold? Because so far we have connections and curvature living here, and I said, I didn't actually prove, that they represent the interacting fields down here. So I should show that. So how do we go back to a manifold? We need a map to go back to, because this map is not useful, because this just, this flattens the whole space. This erases all the information, all the structure gets flattened and you lose it. So you need something that reliably tells you what's going on up here. And this is called a section. Sections are very natural things, but if you have the tangent bundle in mind, so the one that you showed with the sphere and the tangent vectors, a section is just a vector field. So if you have this intuition for vector fields, sections will be very obvious. Okay, so sections essentially maps that take your points from M to P, and in such a way that when you project that back to the base manifold, you get the same point. Okay, so it's something like having an embedding of M on P. Like M is straight and here it's like a curved surface, something like that. Now, if we take a local section, oh, by the way, there's a result that you can only define global sections, so global such maps, if the bundle is trivial, even only if the bundle is trivial. That's important. So that's why I'm working always with a neighborhood U. So if you take another one, another section that is defined by the action of this of this Gates transformation. That just means that at every single point, the value of sigma is active with this group element. So if the value is this thing, then, I mean, this is the value of sigma of m, then if you have a Gates transformation defined in this region, then you get another point on the same fiber, which is just g times g of m times sigma of m, right? It's the natural way to define the transformation or the action of a Gates transformation in between sections. But now, these maps allow us to pull back any tensorial object that we have up here, and that is the connection and the coefficient forms that we already defined. So we are to pull back these connections, this connection form. So this connection form is the one living in the Ferri bundle with the pullback of the map. This is the usual pullback as in differential geometry. And so we get what is called the local representative of a connection form. That lives obviously only in this open neighborhood, but again, if your Ferri bundle is trivial, you can do that in the whole space. So the requirement that they come from the same object, not some argument about invariance or anything, just the fact that they come from the same object, the original omega, but they're just two representatives using two arbitrary G-related sections, mean that they have this transformation law. And they say, okay, that's not familiar to me. It's actually quite geometric phrasing of a Gates transformation. But if I write that in the matrix notation, or indeed if the Gates group is a matrix group, in which case the formula will be actually true, this is the root. And I hope you all recognize this transformation law. And of course, this and this are just the local representative of the connection, and that's what we call the Gates potentials. So let's see some examples. We have that, and consider, so let me go here. Consider the case of electromagnetism, and in electromagnetism, we have a gauge transformation that is something like this, right? We all know that it depends, like phase assigned to every point of space. And in GR, the freedom of choice of a chart is encoded effectively as in, you know, if you have two charts, then in the overlap you have the Jacobian of that coordinate change. And so this thing for the GR setting would be just a Jacobian, so some kind of, you know, still, something like this. So if you bear this in mind and you just plug those formulas, you take into account that these are actually matrices, because you know the algebra of a matrix group is just the subspace of the matrix algebra. So you actually multiply matrices and computing differentials as, you know, differentials of the matrix entries. You get precisely this, which is very familiar and very, you know, from our daily computations in physics. So you get the transformation of electromagnetic potentials, these are just the omegas, and the transformation of the connection forms. So it's, I think this is, I mean, this is the pinnacle of my talk, to show you that all these geometric constructions actually recover the usual Gates transformations. And maybe something surprising to someone could be that the GR is actually just a very kind of formulation of electromagnetism or Young-Mills, just with a different structure group. So let me finish with some conclusions. So first of all, we justify that in QFT or symmetries when we dealt with Gates transformations, we always worked with things like this, as I said before, etc. And so we're always using some chart, some coordinate basis. Why is that licit? Why can you do that always? Because the Young-Mills theories that we dealt with were trivially defined. So they define a trivial bundle. They're just a direct product of space-time and the Gates group. So there's no problem in defining global sections. Now, that's one point. Another interesting point that I find myself is that it provides a very systematic procedure to define new theories. So if you're a theorist and you have some phenomena that you don't understand, and you just have electromagnetism, or someone told you, well, gauge theories are this. So you actually have a systematic way of, you know, by trial and error, you can define all the theories that you wanted. Like, I mean, if you fix the base space being space-time, which might not be the case, but if you fix that, then you have the freedom of defining G, any group you want, and then for different G's you will get different dynamics. So you will get different equations relating curvature and connection and different gauge transformations. So you have a systematic way of defining new theories, which is, I think, very powerful. And then, as I said in the beginning, matter was not considered. So I only talk about the field equations. No matter was involved. So the current was, you know, set apart. So now this setting provides a very natural, you know, formalism for the introduction of matter, and that is associated vector bundle. So an associated vector bundle, essentially, or an associated bundle, is just a bundle over the same basis space, on which the structure group of this principal bundle acts on the fiber. And so if you have a matrix group, then the fibers are indeed just vector spaces. And for example, for the UN case, the fibers are the vector spaces of complex n-dimensional arrays of values. So it's a natural way to see, for example, spinors or wave function, complex wave functions. And indeed also matter in GR, like T, you can regard it as a scalar being valued in the matrix space. There are several ways to regard matter, and it provides, it's not the only one, it's not the best, I'm not trying to argue that, but it provides a natural setting for matter interaction, for field matter interaction. And finally, there are some developments, some discoveries that were actually possible because of this formalism, or at least that were easily understood in this context. One is monopoles, another is charge discretization of monopoles, and anomalies are actually also systematically studied in this context. So yes, there's some advantages that are specific of this formalism, and that's what I basically wanted to say. Thank you very much.
Any questions?
Yes.
Yes.
Are you attending differential geometry?
Yes.
Yeah, I suppose that because in differential geometry we saw like connection forms in vector bundle.
Yeah.
I suppose that these are like one-to-one related to if I construct the vector bundle associated to this principal bundle.
Probably.
The horizontal choice in the principal bundle should give me an horizontal.
Probably, yes. I'm not sure, I haven't done that. Probably. Yes?
Just you said that it can be used to study new things, such as magnetic monopoles.
Yeah.
How exactly, like what can you
Okay,
find?
I was expecting that question. So, it's a very nice, the magnetic monopoles is, so let me go back maybe to the very beginning. So the basic idea about magnetic monopoles is that you assume an extra charge on your theory. So when you, so this zero there, you change into something and then you add some magnetic current there. And the basic point about magnetic monopoles is that there are some topologic limitations for them. So if you assume that you have some electric current and you have some charge on your space, it's a matter of just the homology of four-dimensional affine space, that you can only have one kind of sources in these sort of equations. Because, and the point is, if your manifold is four-dimensional affine space, so Minkowski space, so now in the language of differential forms, you can always do this. You can always write that. And now, if I phrase this in the differential forms language, if your manifold is this by Poincare lemma, this is always possible. So, introducing magnetic monopoles or magnetic charges will be equivalent to setting some, K here, some magnetic current there. But the problem is that if you're working on sorry, Minkowski space, this is always the case, and so this is always the case. I mean, obviously. Right? So there's a problem. If you want to stick to smooth fields, you cannot have monopoles. I mean, working on Minkowski space. If you're restricted, so how this was, you can go around that, but say that your fields are not smooth, so you have singularities and this sort of stuff, and then monopoles appear. But if you stick to smooth fields, you cannot have monopoles. So, but what you can do is that if you change M and you for example remove the origin from R3 and become something topologically non-trivial, then it becomes possible to have monopoles like that. Because otherwise you have an abstraction from Poincaré-Lima that you cannot have monopoles like this. I mean, the precise way to go is actually you see the four-dimensional spacetime as something like this, and then you actually compute integrals, and you see that actually not only that you have monopoles, but the charge is discretized, so that you have integer values.
So is that to say that magnetic monopoles don't live in Minkowski space? If they were found, it means we live somewhere else?
I mean, you get two perspectives. So if you want to understand monopoles as in a smooth field theory, which is the case for all these geometric treatment. I mean, the geometric treatment has the advantage of being very powerful, but it's got the drawback that everything should be smooth or differential to some order. So if you want to use this kind of formalism, if you work on Minkowski space, you won't find any monopoles. So if we did find some monopoles, then you maybe say, okay, so our spacetime is not trivial. I mean, if you stick to the formalism of smooth. Yeah, thank you.
Thanks.
So
Yes.
I think in GR, the basic object is actually the metric tensor instead of the connection, and
Yeah.
that actually imposes extra conditions on your
Definitely.
connection, such as the symmetry or something like that.
Yes.
So can you actually still regard that as a specific example of gauge theory?
Yeah, so of course I was waiting that question as well. So essentially what you do is you restrict yourself to a sub-bundle of, instead of the general GL4, you consider a sub-bundle that actually makes sense of this metric as some sub-bundle that leaves the metric unchanged. So you start off from a Riemannian manifold with a metric, a Lorentzian metric, and then you build the bundle of instead of considering GL4, you consider the Lorentz group at every point, and then you get an equivalent formulation. And actually, I'm not sure right now if what you get is the same formulation but with a metric compatible connection, or what you get is directly all the equations for the Christoffel symbols and geodesics. But I think it should be possible. Should be. I haven't looked into the details.
I think there's a problem because, I mean, when you try to define the Lorentz group at each point, you already have a metric tensor.
Yes.
But presumably you want to set up the system in a way such that the metric is not known a priori.
Yes. But I think the way to go is, okay, so you don't know the metric, but you know that once the connection is, essentially if you have a metric on your spacetime, and then you consider a connection on some bundle that should be metric equivalent when projected, then probably, that imposes some conditions on the initial connection on your fiber bundle, and then that connection is your dynamical object from that point. And it's not the metric, but it's completely tied down to the metric itself. So probably you I'm not sure about this, and I didn't actually study this in detail. So I just realized that, okay, so a fine connection, the theory of affine connections on a Riemannian manifold, on a four-dimensional manifold could be regarded as a gauge theory. But relativity as the full theory, as a gauge theory, I don't have the precise formulation. I don't know. So maybe there are some problems.
I think the connection has got much more degrees of freedom than a metric tensor. So,
So it should be like, in general relativity, you can in general choose a you create a connection, and there is a natural connection that you can choose. That is the one that behaves well with the metric tensor and stuff. So it's like I guess the theory with a natural choice of connection.
You don't have to pick a metric compatible connection. It is
Yeah.
natural. And then if you are talking about, if you are picking a metric compatible connection, I think it's probably equivalent to saying that you're reducing the structure group from GL4 to the Lorentz group, say.
Yes.
But you don't need the metric and the space-time to say that. You just need to say that you only allow a structure group which happens to preserve the flat Minkowski metric. And then you can see what that implies for your connections, because they have to be compatible with that source of structure group. Well, I think we've run out of time for questions. But
Yeah,
there'll
we
be a
can discuss
coffee-
afterwards.
There'll be a coffee break in 45 minutes,
Yeah.
which is going to continue with any questions. So let's thank Carlos again.
Thank you very much.